Hi everyone, welcome back. In this lesson, we're going to learn about writing chemical formulas and chemical nomenclature. So first, let's start off with talking about what a chemical formula is. So a chemical formula is a notation that scientists use to show the types and the number of atoms of each type that are present in a molecule or a compound. So what we see down here, these here are chemical formulas. As you can see, they use atomic symbols, right? Na here for sodium, O for oxygen, to show what type of atoms are present. And what you notice is that following each of the symbols, there is a subscript. In this case, there's no subscript present. If there's no subscript present, it means that it's a 1, not a 0, but a 1. The subscript indicates how many of that atom are present. So the subscript follows the element symbols. So the 2 here represents that there's 2 sodiums present and 1 oxygen present. Here we have 2 carbons and 6 hydrogens. Here we have 1 sulfur and 3 oxygens. In this lesson, we're going to be looking at writing formulas for ionic compounds. We're not going to be looking at molecular compounds as they're not as predictable and much more difficult to write formulas for. So we talked about this before, that ionic compounds are formed from positive and negative repeating units, and they form this lattice structure. So they're charge neutral, meaning the number of positive charges balances the number of negative charges. And in ionic compounds, the cations, which are usually the metals, combine with anions, which are the nonmetals, in whole number ratios. So we have NaCl, which is 1 Na for 1 Cl, calcium chloride, which is 1 calcium for 2 chlorides, or sodium oxide, 2 sodiums for 1 oxygen. Notice that these are whole numbers. We don't have, for example, half of a sodium with half of a chlorine. Ionic compounds have to be written in simple forms, in the simplest forms. So we don't write them as, for example, Mg2O2. We reduce that to MgO. So we always reduce it. And if you remember, we call that smallest whole number ratio a formula unit. So let's go ahead and look at rules for writing formulas for ionic compounds. And the method that I'm going to show you here is called the crisscross method. So for the crisscross method, we're always going to start off with the cation first, because in the chemical formula, the cation is always written first. So we write the cation first, and we put the charge that it would have in a compound in the upper right-hand corner. So in the example we're looking at, calcium is in group 2A. So calcium has 2 valence electrons that it would like to lose, so it would get a charge of +2. Then we write the anion, which is usually the nonmetal. We write the symbol for it, and we put the charge that it would like to have in the upper right-hand corner as well. And then we just cross over their charges. So the superscript that was the charge of the cation now becomes the subscript of the anion, and vice versa. So the -1 here from the chlorine now becomes the 1 for the calcium as its subscript. Any ones we get rid of, it's just implied that if there's no number following the symbol, that it is a 1. And you simplify it if it's necessary. So if you ended up, for example, with Mg2O2, you reduce that to MgO. Now what we're going to look at is nomenclature, or systematic names for ions and compounds. So let's go ahead and start with naming ions. And we'll specifically start with anions first. So to name an anion, or give the systematic name for an anion, we first write the base name followed by the suffix IDE. So here in this table, I give you the nonmetal, the name of it as a neutral element, the symbol that it would have for the ion, the base name of it, which this is what you would have to memorize, and then what the name would be after you add the IDE suffix to the base name. So for example, fluorine has the base name fluor. I add the IDE ending and it becomes fluoride. So fluoride is the systematic name for F minus. Let's look at another one. Nitrogen likes to have a charge of -3. Its base name is nitre. And then I add the suffix IDE at the end and it becomes nitride. So for most of them, or for all of them, pretty much the base name is the first part of the name of the nonmetal. If there is an INE at the end, we just drop the INE. If there is an OGEN at the end, we drop that. So for oxygen and hydrogen, we drop that GEN at the end, or OGGEN at the end. For fluorine, chlorine, bromine, iodine, we drop the INE at the end and add the IDE to it to give the name of the anion. All right, so now we're going to move on to naming cations. There's two different types of cations. There are type 1 cations and there's type 2 cations. So we're going to start off with type 1 cations. Type 1 cations have one possible charge. So they always have one possible charge and it's always the same charge, as opposed to type 2 cations, which we're going to look at next, which can actually have more than one charge. The type 1 cations include the group 1A metals, so lithium, sodium, potassium, rubidium, cesium, and francium. All of the type 2A metals, beryllium to barium. Aluminum, which would like to have a charge of 3 plus, zinc, silver, and cadmium. So remember that the group 1A metals want to have a charge of +1. So these metals will always be +1. Their charge will always be +1, and they cannot have any other charges if they're part of a compound. Group 2A metals in a compound or as ions always want to have a charge of +2, and there's no other charges that they can have. Aluminum is in group 3A. It wants to have a charge of 3 plus because it likes to lose 3 electrons. And then we have zinc, silver, and cadmium, which actually are transition metals, so their charges are not as easy to predict, and so you have to memorize these three. Zinc will always like to be +2 as its charge as an ion. Silver always wants to be +1, and cadmium always wants to be +2. So you just have to memorize those three. They're the only transition metals that are part of the type 1 group. An easy way to spot them is notice they're all next to each other, so it's zinc, silver, and cadmium. And if you notice, they make a little triangle. So if you can spot this triangle on the periodic table, you'll know that these three are part of the type 1 cations. So we know that the group 1A metals want to be +1, group 2A metals want to be +2, aluminum wants to be +3, and then we have these three transition metals where zinc wants to be +2, cadmium wants to be +2, and silver wants to be +1. So the way that we name these cations, the ones that are type 1, is all we do is give the name of the element and then write the word ion following it. So sodium is the name of the neutral form of Na, and then when it becomes Na plus 1, we name it as sodium ion. Zinc, for example, has a charge of +2 as an ion, so we name it as zinc ion. Notice that for this type 1 cations, there is no mention of what the charge is when we give its systematic name, right? So even though the zinc here is +2, for example, we just write zinc ion as its name. We don't mention anything about its charge because zinc always has to have a +2 charge. So in order to give the name of these type 1 cations, you do have to have some prior knowledge and background in chemistry and know what charges those metals like to form. Okay, so now we're going to continue on with looking at type 2 cations. Type 2 cations are ions that have more than one possible charge. Okay, so for example, as we're going to see in a second, chromium can either be +2 or +3. Sometimes it's +2, other times it's +3. And so these cations have more than one charge, or they can have more than one charge. And so as a result, when we name these, we will have to mention something about their charge so that we know which cation we're referring to. The type 2 cations are mostly part of the transition metals, with the exception of silver, cadmium, and zinc, which we looked at are type 1. But in addition to the rest of the transition metals, tin, which has this symbol SN, and lead, which has the symbol PB, are also part of the type 2 cations, meaning these also have variable charges. So we see here that tin, and I put a star next to these, the ones that have the star next to them, indicates that they are not transition metals. Tin can be either +2 or +4. Same thing with lead, Pb can be +2 or +4. Okay, so you would actually have to memorize in order to know which charge each cation forms. Notice that manganese, for example, is +1 and +2, but then gold is +1 or +3. So there's no way to really predict it unless you memorize it. Now, to give the name, the systematic name for type 2 cations, you have to not only give the element name, but you have to give the charge that that cation is forming. And you do that by following the name of the atom with parentheses Roman numeral, parentheses closed, and the Roman numeral tells us the charge that that cation will have. So chromium 2 plus is chromium 2, and it's optional to write the word ion at the end. It's not mandatory because the Roman numeral already tells us that it's an ion because it's referring to the charge. Here we have cobalt 3 plus, so I write it as cobalt, Roman numeral 3. Tin 2 plus, I write it as tin, Roman numeral 2, right? And I can follow it by the word ion if I want to. But notice that for the type 2 cations, we have to specify the charge as Roman numerals because these can have variable charges. So if I just said tin ion, you wouldn't know if I'm referring to tin with a 2 plus charge or a tin with a 4 plus charge. So it's important to specify which of those charges we're referring to. And then there's another group of ions called polyatomic ions. And what you may notice about these polyatomic ions is that they are treated as a unit, even though it's a combination of multiple elements linked together. So you would be required to memorize this chart, or depending on what your instructor says, partially, or there could be more added to this. There is another video that'll show you how to memorize it and give you some mnemonics for memorizing it more easily. But notice that a lot of these end in ATE, so acetate, carbonate, nitrate, or they end in ITE, nitrite, for example, okay, sulfite. And just one thing to note is that if they end in ITE, the ITE contains one less oxygen than the ATE. So that's one way to remember these. And we treat these as a unit. So the O and the H, for example, here do not break apart from each other. This OH together has a -1 charge. Or here the CrO4 together has a -2 charge. So this entire substance occurs as a unit. And so if this, for example, is linked to, let's say, sodium, this would require 2 sodiums for 1 chromate. Let's say if we have a hydroxide linked to a magnesium, we would have Mg, and then we would put the OH in parentheses, and then put the 2 outside of the parentheses to show that there are 2 hydroxides for 1 magnesium. So if more than one of these polyatomic ions occurs in our chemical formula, then we have to put it inside of the parentheses before writing the subscript of how many of it occurs in that compound. Right. Next, we're going to look at naming compounds. Remember that compounds are pure substances that are made up of two or more different types of elements. So there's two different types of compounds. There's molecular compounds and there's ionic compounds. First, we're going to look at molecular compounds and then we'll look at ionic compounds. So remember, molecular compounds can be made up of a metalloid and a nonmetal, or they can be two nonmetals joined together. Whereas ionic compounds are made up of a metal plus a nonmetal. So the way that we name compounds is the same skeletal structure for all of them. First, we give the first element name, followed by the second element base name, and then we add IDE. Okay, so they all follow this skeletal structures, and then these two red lines and the blue line here could be extra things that we would add to it depending on whether or not it's a molecular compound or a type of ionic compound. All right, so we're going to begin with naming molecular compounds. So to name molecular compounds, what we do is we take that equation that we had for naming compounds and we add a prefix right before naming the first element and a prefix right before naming the second element. And the prefix stands for the number of that element that's present. For example, N2O5 would be named as dinitrogen pentoxide. The di because there are two nitrogens there, and the pent because there are 5 oxygens there. We use the prefixes that are given over here. Now remember that molecules can be made up of either a metalloid or a nonmetal, in which case the metalloid is named first, or they can be made up of two nonmetals, and in that case we follow the order of the nonmetals here, and the one that's named first is the one that has the higher priority. So carbon has the highest priority of the nonmetals in terms of being named, then phosphorus, nitrogen, selenium, hydrogen, sulfur, iodine, bromine, chlorine, oxygen, and fluorine. Where this comes from, this order, a good way for you to remember is that if we take all the nonmetals that can make a compound on the periodic table, with the exception of hydrogen and oxygen, from left to right, bottom up on the periodic table, determines the order. So carbon is the leftmost nonmetal, so carbon first, and then phosphorus, nitrogen, and then SES, and I, Br, Cl, F. And then you just have to remember that hydrogen goes in between S and Se over here, and oxygen goes between Cl and F over here. And then the last rule is that if mono is the prefix at the very beginning of the first element, then we just drop it. So for example, instead of saying monocarbon dioxide, we just name it as carbon dioxide. We do not include mono if it's at the beginning of the first element. All right, now we're going to move on and look at naming type 1 ionic compounds. So remember that type 1 ionic compounds are compounds that are made up of type 1 ions. Remember that the type 1 ions contain cations with only one possible charge. So to name them, we just use the equation as is. We don't add any prefixes or Roman numerals or anything. We just name the first element and then the base name of the second element, IDE. So the type 1 ionic compounds contain one of the cations from either group 1A, 2A, could be aluminum, zinc, silver, or cadmium. So here are two examples. For example, if we have Na2O, we just name this as sodium oxide. So we give the name of the first element, base name of the second, IDE ending. Notice that there is no mention of the 2 that's there. And the reason for that is just because sodium will always have to be +1 and oxygen will be -2 if it's with sodium. So there's no need for us to say that there's 2 sodiums present.
So we need to know enough chemistry to know that the only way that sodium and oxygen can come together is if there's two sodiums for one oxygen. Another example, AlCl3 is named as aluminum chloride. So we do not mention anything about the fact that there are three chlorines present. Right, so now we'll look at type 2 ionic compounds. For naming type 2 ionic compounds, we add a Roman numeral to the skeletal equation that we had. And remember that type 2 ionic compounds contain type 2 metals. And remember that type 2 metals could have more than one possible charge. So the reason we need to have a Roman numeral is to show what that charge of the cation is, because it could be two or more potential charges. So the type 2 cations could be either one of the transition metals, with the exception of silver, cadmium, and zinc, which we said always have a single same charge, plus tin and lead, which could also have variable charges, which are not part of the transition metals. So in order to figure out what the Roman numeral would be, we need to determine what the charge of the metal would be. So we would determine the charge of the metal based on the nonmetal that's attached to it. So for example, in FeCl3, we know that because chlorine is a group 7 element, it wants to have a charge of -1 to be like the noble gases. Since there are 3 chlorines present, that would mean that the iron has a charge of +3 in order to neutralize this compound. And so we would name this as iron 3 chloride. You'll notice that oftentimes the Roman numeral is the same as the subscript of the nonmetal, but that is not always true. For example, in the case of MnO, the subscript of the oxygen is 1, but the Roman numeral is 2 for manganese. And that's because the oxygen here has a charge of -2, and so the manganese is +2. So we name this as manganese Roman numeral 2 oxide. And then for naming ionic compounds that contain polyatomic ions in them, it's the same rule, really, for those ionic compounds, except wherever the polyatomic ion occurs, you put the name of that polyatomic ion without modifying it. So we can have either a type 1 or a type 2 metal bound to a polyatomic ion. So same rule applies for naming it. And then we just put the name of the polyatomic ion. So we wouldn't add where the polyatomic ion occurs, we would not add the ending IDE to it if it's a polyatomic ion. If two polyatomic ions occur together, like this bottom one here, we just put the name of the two polyatomic ions. And then if it's a polyatomic ion, which actually this case only occurs if we have ammonium, okay, as that was the only one that I gave you on that list, then you would just name it as ammonium, and then you would give the name of the anion just like we learned before with giving the base name IDE. So here are the 3 examples of the 3 rules that I put above. So here we have lead 4 sulfate. I know that the lead is a 4 because each SO4 is -2 and there's 2 of them. That makes -4, so this is lead 4 sulfate. Ammonium is +1, chloride -1, it's just ammonium chloride. And here, carbonate is -2, ammonium +1, but notice there is no mention of their charge. I just put the name of the polyatomic ion where it occurs. So now we're going to talk a little bit about acids and bases before we learn how to name them. So acids contain hydrogen. And when we put acids in water, they produce H+, which is actually just a proton in water. So that proton becomes attached to water and it actually forms an H3O+, which we call a hydronium ion. Acids neutralize bases. And again, when we put them in water, they break up into H+ and Cl-. We always put the ionizable hydrogen first. The ionizable hydrogen is the hydrogen that breaks up into H+ when it's placed in water. Bases, on the other hand, produce hydroxide ions when they're placed in water. And bases neutralize acids, and that's because the hydroxide that's produced from the base combines with the hydronium, or the H plus that's produced by the acid, and it forms a water molecule. And that's how they neutralize each other. Many bases, but not all of them, are made up of a metal that's attached to a hydroxide. So for example, sodium hydroxide, NaOH, is a metal, sodium, attached to a hydroxide. So then when they are placed in water, the hydroxide that's attached to the metal just breaks off. Other forms of bases produce hydroxide not because they contain a hydroxide within their formula, but because when they are placed in water, they take away an H plus from water and leave behind a hydroxide, an OH minus, that belong to water. So here, NH3 is called ammonia. When ammonia is placed in water, it takes an H plus from the water molecule, forms what we call ammonium, and it leaves behind a hydroxide that belonged to that water molecule. But in either case, because it produces a hydroxide in water, it's still considered a base. Now going back to acids, there's two different types of acids. There's inorganic binary acids and there's oxyacids. The inorganic binary acids are acids that only contain a hydrogen attached to some form of a nonmetal, or in some cases a polyatomic ion that has no oxygen. In order to be an inorganic binary acid, it does not contain any oxygen. These inorganic binary acids have to be in water in order to be considered acids. Otherwise, they're just considered molecular compounds. So we would have to write AQ following the chemical formula of the acid. For example, HClAQ is an acid, it's a binary acid. HBrAQ is a binary acid, and HCnAQ is a binary acid. If I don't include the AQ, then it is not an acid. It would just be a molecular compound, and for example, we would name it as hydrogen chloride. But if it has the AQ at the end, then it would be considered an acid. The second type of an acid is called an oxyacid, and the oxyacids contain oxygen in them. And usually the oxyacids are a hydrogen attached to a polyatomic ion that contains an oxygen in it. With the oxyacids, almost all of them have to be in water. They can't just be pure, except for acetic acid. The only one that we can have a pure form of it is acetic acid. So for acetic acid only, in order for it to be considered an acid, it needs to be followed by AQ. Otherwise, with the other oxyacids, we do not have to write AQ following the name. It's just implied that they occur in water. So we still name them as an acid, even if it doesn't say AQ. However, for the binary acid, it has to say AQ in order for it to be named as an acid. So let's begin by naming binary acids, the ones that do not contain any oxygen in them. The formula for it is we put hydro at the beginning, followed by the base name of the nonmetal, adding the suffix ic, plus acid. So HClAQ would be named as hydrochloric acid. Okay? HBrAQ would be hydrobromic acid. So the word hydro, or the prefix hydro, is added only to the beginning of the binary acids, which are the ones that do not contain any oxygen in them. For the oxyacids, on the other hand, the ones that do contain an oxygen in them, there's two different rules that we would have to follow for naming them. And that rule depends on what type of a polyatomic ion is attached to the hydrogen. If the polyatomic ion that's attached to the hydrogen ends in ATE, for example, in this case, we have nitrate, attached to our hydrogen. If the polyatomic ions ends in ate, then we name it by the base name of the anion followed by the suffix "ic" plus the word acid. So this would be named as, it's a nitrate, so we'd say nitric acid. Notice that for the oxyacids, we do not use hydro as a prefix. And then for the ones where the acid contains a polyatomic ion that ends in ite, for example, SO3 2- is sulfite. If it ends in ite, then we name it as the base name of the oxyanion OUS. We add the OUS suffix and then the word acid. So this is sulfite. It becomes sulfurous acid. Okay, so for the oxyacids, pay attention to the polyatomic ion and see whether or not it ends in ate or ite, and then follow the correct rule. And then here's just the mnemonics for you to remember naming acids. For the binary acids that do not contain any oxygen in them, if you remember the sentence, my ride has hydraulics, okay, what this is telling us is that when the nonmetal that's attached to the hydrogen ends in IDE, here chloride, then we do hydroic acid. So hydrochloric acid, okay? If you remember, I ate something icky. If the polyatomic ion ends in ate, then we put the suffix ic. Okay, so here we have H2SO4. It contains sulfate in it. This is sulfate. So it becomes sulfuric acid. And then if you remember, Sprite is delicious. Okay, if the polyatomic ion attached to the hydrogen ends in ite, like sulfite, then we put the suffix us, OUS, acid, so sulfurous acid. Right? And then we're going to look at naming hydrates. So hydrates are ionic compounds. So remember, they are pure substances that have water molecules bonded to them chemically. So they're the ones that have the ionic compound form dot some number of H2O. In order to name them, we just name them the same way as we would name the ionic compound. And then for the number of water molecules attached to it, we would put a prefix, okay, for the number of water molecules, followed by the word hydrate. And the prefix indicates how many water molecules there are. So for example, CuSO4.5H2O, we first name this ionic compound. Notice it's a type 2 because copper is a type 2 ion. So we name it as copper, Roman numeral 2, sulfate, and then pentahydrate. Penta because there are 5 water molecules. So we use the prefix pentahydrate. Right, so now we're done with this lesson. Here are some practice problems for you to attempt, and the answers are on the next page. So you can pause this video, do these problems on your own, and then check your answers on the next page. And then here are the answers to the questions on the previous slide.